Now, going back to our graph of f of x equals 3 divided by x over, or x minus 2. In this picture, notice I have drawn in that line of x equals 2, which hopefully we know is called an asymptote, and it's called a vertical asymptote in this case because it is a vertical line. Again, whenever we have a function that's going to approach infinity or negative infinity, typically we have a vertical asymptote. So where this would not be the case is, let's say I had a function that looked like this. I might end up in this case with a slant asymptote instead of a vertical asymptote, but in this case typically we're going to end up with a vertical asymptote. And that is just a line where our function gets closer and closer and closer to, but never touches. So I know that in previous classes, MA 102 for sure, you have talked about how to calculate vertical asymptotes. But hey, let's just review it real quick in case you haven't had that in a while. Let's say I have a function f of x equals x plus 2 over x plus 2x minus 1. So obviously, if I were looking at this function, there are 2 points of discontinuity. And we'll talk about which one's removable and which one's an asymptote. So if it's something where I'm actually able to do some reduction, this would be a removable discontinuity at x equals negative 2. And again, that's because I could just define the function at that point and we'd be okay. However, x minus 1 did not cancel. And so what I know about x minus 1 is, of course, if I set that equal to 0, I get x equals 1. This is a vertical asymptote. So again, it's where the denominator is equal to 0, but where the numerator would not also be equal to 0. Or essentially just look at what is going to cancel. So let's do a little bit of practice. Again, do your factorization whenever necessary, which will be the case here. Try all 4 of these, then press play to see how you did. So for my first guy, this one's pretty straightforward. All I would have to do is say, hey, x plus 1 can't be equal to 0, so therefore x cannot be equal to negative 1. I didn't have to do any work there. For my second one, you would like to think that there would be some cancellations that would happen with my numerator, but unfortunately x squared plus 1 doesn't factor, and this does factor by difference of squares pattern into x plus 1, x minus 1, and therefore positive and negative 1 would not be okay. And they would both end up being asymptotes, of course, because nothing canceled. For cotangent, again, that's just you knowing what cotangent is all about, which is cosine divided by sine. We know that sine of x can be equal to 0, and sine is 0 at pi and all the multiples of pi. So it's where x is equal to pi times n, where n is a whole number. And I should have included n is an integer. Last one, again, this is where you would want to do some factoring. This obviously is x plus 2, x minus 2, difference of squares pattern. The numerator would be x plus 4, x minus 2. And the x minus 2's cancel, so that is not an asymptote, that is just a whole at x equals 2, which means my asymptote would be at x equals negative 2, because I would say x plus 2 can't be 0, x cannot be negative 2. Before we finish up section 1.5, let's talk a little bit about some properties of infinite limits. Again, most of these are pretty commonsensical, pretty straightforward. This is saying if the limit as we approach c of f of x is infinity and of some other function g of x is L, meaning it's just some number, and it doesn't matter what the number is. You can plug in a number 2 or 3 or 7 or 19 or whatever, floats your boat. essentially what we're saying is if you're adding the limit of f of x to the limit of g of x, it's going to be infinity, which makes sense because infinity is a large number, and if I add 2 to it, it's still infinity. Same thing with multiplication. If my limit is positive, if I take some number times infinity, I get infinity. If I take some number that's negative times infinity, then I'll get negative infinity. And again, quotient of some number, again, it doesn't matter what the number is, divided by infinity would be 0, because as I divide by a very, very large number, I'm going to get closer and closer to 0. Okay, let's look at these last 3 questions together. Use those properties of infinite limits, use your brain, use your calculators. Press pause, do all 3, then press play to see how you did. So first let's look at A. And again, use just what we know, which means I can find the limit as x approaches 0 of 1 is 1. But if I try to do direct substitution for 1 over x squared, it's not going to work. So what I want to think about is what is going to happen if I take 1 divided by an increasingly small value. Because again, it's not 0, it's as I approach 0. So as I approach 0 from the left, or approach 0 from the right, I'm going to have a very, very small number, and I'm going to square that very small number, and I'm going to take 1 divided by a really small number, which is going to give me a really large number, which is going to approach infinity. Again, you can also graph that and take a look at what 1 over x squared looks like, and we can see that it's going to approach infinity from the left or from the right, which is why this is not a one-sided limit, it's just 0. And essentially then what I'm doing is taking 1 plus infinity, which our limit properties say that's infinity. Looking at the next one, again, I can use direct substitution even though it's one-sided. I can use direct substitution on the top. 1 squared plus 1 is 2. On the bottom, however, I'm looking at the cotangent of pi times x, which is pi times 1. So basically I'm saying as I get closer and closer to pi, what is the value of cotangent? And what I find is that value is negative infinity. And so what I'm looking at is 2 divided by a really, really large number. So here I was dividing by a really, really small number and got a really large number. Now I'm dividing by a really, really large number and I'm getting a really small number known as 0. Last one, limit as x approaches 0 from the right. Again, the limit of 3 would be 3, but the limit of cotangent of as I approach 0, again, you can verify by graphing. That is infinity. Again, from the right-hand side, it is positive infinity, and so 3 times infinity is just infinity.